Sometimes you find that pieces of a circuit can be simplified. For example, here we have this section here, which looks pretty complicated. And the idea is that you have the rest of the circuit over on this side and over here connected to it. But there's a section of the circuit which can be sort of siphoned off by itself with just two connections. Now, the idea is that all of those resistors could be replaced by a single resistor. And the reason this is so is that if you think about the current flowing into this and back out over here, which we know has to be equal, and if we took the voltage from one terminal to the other, we expect that that current and voltage are proportional to each other. And the ratio, the voltage over the resistance, over the current, is the resistance. So that's what we hope to do, is find what value of resistance would be equal to all of those resistors over on this side combined. Okay, so we do this analysis by pieces, and the first thing we're going to do is we're going to just focus on these two resistors right here. Now, to generalize this a little bit, they might not have been the same value of resistance, so I'm going to draw them as two different resistors. Okay, and imagine that there's two connections, like there was in the other one, to those two resistors. Okay, so if we look back up here, there's the two resistors and they have some connection going to the rest of the circuit. So we'll say that this one has a resistance R1, this has a resistance R2, and that the voltage from one end to the other is V, whereas the voltage on these are V1 and V2. All right, the most important thing about these particular two resistors is that if we look at this junction here in the center, there's no other resistors connected or any other wires, and therefore we know that the current in those two resistors is the same. So what we find is there is a single current that goes all the way through the whole circuit. Okay, so we could write that down. And anytime that this happens, any two circuit elements that have the same current we say that they're in series. And this analysis that we're about to do will always apply for resistors in series, that is, having the same current. All right, so the next step is, once you've noticed that they have the same current, is we take a Kirchhoff's voltage loop, sort of around like this. Okay, so we go through the voltage from the lower terminal to the upper terminal. Through this one we drop from V1 upper end to lower end, then V2 upper end to lower end. So we get this equation like that. And now we could rewrite this. And we can use Ohm's law. And then we notice that those two currents are the same because they're in series. And that's the current going into the whole system. And then the resistance of these, the effective resistance of those in series, is just the voltage divided by the current, which is just R1 plus R2. So this is the main result here, that if you have two resistors in series, you can replace them with a single resistor that's just has a value that's the sum of the other two resistors. Okay, so let's see what this would allow us to do with this circuit here. So now we could take these two resistors here, get rid of them, and replace them by a single resistor, where that resistance is the sum of the two resistances. In this case, they were both the same, so we'll just say that one has a resistance of 2R. Now we notice that there's other resistors in series. See, these two are in series, these two are in series, and these two are in series. So we can go through one at a time and get rid of those and replace them with something that looks simpler. Oops. Okay, so now our circuit's a little more simple. All right, so at this point there are no more resistors in series, so we can't simplify it further in that way. We know that's true because if you look at this junction here, there's 3 wires going in. So none of those 3 have the same current. All right, but there is something we can simplify. We'll take this section now, okay, and do a similar analysis. So we go down here, and we're going to do something similar. We'll say we'll have a resistor, R1, and then we'll have another resistor, R2. You see, it's the same. They're just they're connected at the ends. Okay, again, we imagine that we know that voltage across there. We think of the current coming in. Now they don't have the same current anymore. The current splits. Okay, so we put voltages on here, and we mark the direction of the voltage difference. Now we notice right away that in this case, if we do a Kirchhoff's loop rule here, around for this one, we go up through the first voltage and down through the second one, and we're back to where we started. The same thing for the other one. We could go up through the first voltage, around here, around this way, and back down. And we get the second equation. So what we find now is that this voltage is V1 and it's also V2. All of the voltages are the same. All right, so this is what we call okay, be careful with the terminology here. In this particular picture in the circuit diagram, the resistors look like they're in parallel, but it's nothing geometric. It's really that the resistors are said to be in parallel if they always have the same voltage on them. Okay, so that's true here, and we'll see why in a second that's important. So now let's write out the junction rule. Okay, so the junction where the two resistors are connected. Now, this current, if we use our relationship between the current and the resistance, should be the effective resistance of the whole thing divided into the voltage, and this will be the same for these two. But since all the voltages are equal, we could also just write this dividing both sides by that voltage. And this is the result we find anytime two resistors are connected in parallel. Parallel meaning that the voltages are equal. All right, so let's look back at our circuit again, the one that we reduced, and see what we can do to this one now. All right, so now we can take these two resistors here and replace them with an equivalent resistance. In this case, we have something that simplifies more than you would normally expect. We find that in this particular case, we end up with just the effective resistance of those two together. It's just the resistance of the original resistor that we started with. So that's just a special case here. But what that allows us to do is get rid of all this mess and put a single resistor in its place. The same over here. Now we see, so that's one stage. We've gone through two stages. We first replaced some that were in series with a single resistor, and now we replaced two that were in parallel with a single resistor. If you look now, we have series resistors again. We can do this in stages or all at once, because we could just add these two to make it a single resistor, and then add that single resistor to the other ones. But in series, if they're all in series, in other words, this resistor, and that resistor all have the same current. So we can do the same thing. We can just add all three without having to go in two stages. So this circuit is equivalent to because when you add resistors in series, you just add the resistances. So those three in a row just act like one with 3 times the resistance. Now you see that we have, once again, two resistors. Now these are in parallel because their ends are connected, and so they have the same voltage. So these could be combined to be a single resistor, where that resistance is found by adding the inverses. Okay. Okay, so those are the general stages. You go, when you're trying to simplify a circuit like that, you go back and forth between getting rid of things that are in series and parallel until you've reduced it as much as you can. It would seem possible that you could always do this until you got things down to one resistor. And it is true that any network of resistors acts as a single resistor. But sometimes you can't use these nice rules about parallel and series to get there. This circuit, for example, doesn't have any resistors in series or in parallel and can't be simplified by this method. You could still do the same thing. Imagine connecting it to a power supply, solve the Kirchhoff's laws, find what the current is, and then you would know what the effective resistance of this is. So it still has an effective resistance, but we can't use these nice simple laws to get there. You have to use Kirchhoff's laws directly. But let's look at an example where we can do it. So let's start with a specific problem with a 10-volt supply. Connected to 3 resistors. Okay, so the first challenge is to decide what can you simplify. Is there any of these resistors that are in series or parallel? All right, so ask yourself that now. And the best thing to do is to look at the junctions. If you can find a junction between 2 resistors where the only thing connected at that junction is those 2 resistors, then those resistors are in series. If you can find 2 resistors where both ends are tied together, so like one end of the resistor is tied and the other end of the resistors are tied, then those are in parallel. In this case, if you look at this junction here, you can see that the only thing going into that junction is those resistors. So that we know that those are in series. They have the same current. So that means we could replace those 2 with a single resistor. So we'll redraw the circuit. We leave this one alone. We leave the power supply alone. But we combine these 2 into a single resistor. Now remember, if they're in series, let's rewrite the rules. If they're in series, we just add their resistances. So we take the 2 and the 4, and we get 6 ohms. Now, if we look at these, we can see that these are in parallel. There's 2 junctions here connecting them. One way to tell is if you go around this Kirchhoff's law, there's only those, Kirchhoff's loop, there's only those 2 voltages, so they have to be equal. And voltages being equal, they have to be equal because they add to 0, so they are, and if the voltages are equal, then you know they're in series. In parallel. So that tells us we can replace that by adding the inverses. So this would be so in the end, we do one more step to simplify. Just have a single resistor of 2 ohms. So then we could check this. So we have 10 volts. These are unknown resistance times 2 ohms. So the current is 5 amps. Okay, so these are very useful. And important thing to remember is they're in series when they have the same current. And they're in parallel when they have the same voltage. Now, surprisingly, it's also possible to do the same thing with capacitors that are connected in series and parallel. And it's the same rule. If they have the same current, they have the same, they're in series. If they have the same voltage, they're in parallel. The one difference is we have to think that if we have, let's just draw it. So we're thinking that these have two capacitors with the same voltage. Okay. Now, the important thing is that the current rule tells us that if there's a charge Q that comes in here, that it breaks up here into two parts. So we end up with Q1 over here and Q2 on that one. And what we know is that that charge must add up to the two individual charges. There's just conservation of charge. No charge builds up here at that junction. Okay, but then we know that that charge is the capacitance times the voltage. But again, this voltage here is the same as the voltage on the C1 and C2. So all those voltages are the same. And so we find that the parallel capacitance is just the sum of the capacitances. Now this is the opposite in a sense of what we had before with the resistors, but really it's not, it's just because of the strangeness of the definitions. If we look at V equals IR and Q is CV, if we wrote this as V is 1 over C times Q, and this is V is R times I, you can see that this 1 over C plays the same role as the R. So we sort of expect, if that's so, that when we do the ones in series, the capacitors will add as the inverses. And indeed, that's what happens. And I'll leave it for you to check that. But if you had two in series, you would find that the series add as the inverses.